Welcome to the Throttle Up podcast, a behind-the-scenes look at what it takes to build and launch a new class of rocket propulsion. Hosted by Sasha Derry, founder and CEO of bluShift Aerospace, and storyteller and entrepreneur Justin Starbird. This podcast follows the real work behind the mission. From early design and propulsion development to testing, capital, partnerships, and the path to launch, each episode brings you inside the process as it unfolds. This is your front row seat to watching bluShift Aerospace take off.
Welcome back to the Throttle Up podcast powered by bluShift Aerospace. My name is Justin Starbird, and today is exciting. I get to welcome Luke Saindon, the lead mechanical engineer, and Gerard Desjardins, the lead propulsion test engineer of bluShift. Guys, thanks for joining me today.
Oh, happy to be here.
Thanks for having us.
I think it's exciting. I see some, neat things behind you, Gerard. That's, in the lab today. I see always a lot going on. No?
Yeah, definitely. Happen to be inside today, fortunately, because it's pretty sunny outside. But I've got some design work to do. And earlier this week, I was outside, and I'm kind of wherever I'm needed.
Right. I mean, Maine in the summer isn't a bad place to be, but I can appreciate, needing to get some work done. Guys, I'm so thankful to have you on today to talk a little bit about, what goes into the build of a rocket. For those that haven't met you, we'll start with you, Luke. What is your role at bluShift? What does a lead mechanical engineer do?
bluShift has been such a small group of folks that you usually end up doing many different things all at once. And our team is sort of growing at the moment, which is really exciting. So people are getting a little bit more specialized. But in the past, my role has been very, jack of all trades, doing a lot of modeling for like performance and trying to predict what the most efficient propulsion unit sizing will be and the performance of the vehicle, and then trying to implement those optimal designs in real hardware and, figuring out what the compromises are. Ideal sizing might not match up to what you're able to do in the real world all the time. So it's a little bit of an iterative process, and then right down to machining and welding the actual parts at times, depending on who's at hand to help do the fabrication, and helping out Gerard running the tests. In the early days, it was me running the tests, or Sasha was also doing a lot of the test work, and we had Brooke, and so we've had different people helping and doing a bunch of the lifting, but I've always jumped around a lot. But get to sort of follow the process from start to finish, right from theoretical optimization right to hardware. And logistics.
It is so exciting to hear like the context, especially, bluShift being a 10-year-old startup, and I'm sure there's a lot that you've seen over the years.
Yeah, it's definitely been lots of different versions of bluShift through the years. It's been a very continuous company that's been at it for a long time, but depending on the circumstances and depending on what specific phase of the effort we're in, it looks like a very different company at different points. So it's you got to be pretty adaptable into terms of what's needed, and it's cyclic. You sort of go through design phases, and then a lot of building, and then a lot of testing, and then a lot of logistics, and then you're usually back to the drawing board for a while. And so,
yeah. Gerard, how about for you as a lead propulsion test engineer? I got to imagine, some of that's in the title, and we can surmise that, but also taking what Luke is sharing and the day-to-day has got to be different all the time.
Yeah, actually, when I first started, 5 years ago this month, my first big task was trying to upgrade our fuel manufacturing procedure. And we went from a 6-inch motor on the Stardust that we launched up in Loring in 2021, and we knew we had to go up to a 24-inch motor. So, kind of adapting our procedures to be able to manufacture our fuel. And then since then, I've picked up a lot of kind of how all the systems work, and now I just jump to wherever I'm needed and do design, manufacturing, testing. Yeah.
Yeah. So, when I think about, rocket propulsion, we think about, engineering and the challenges that go into it, a rocket engine development. It is really sexy, to the outside world, right? Like, so I feel as though that picture sometimes of, when you say that to folks on the outside, they're thinking of the launch itself and seeing this giant, apparatus go into the sky. But for the day-to-day engineering that it actually takes in order to make anything like that happen, you have to actually, Luke, to your point, work on the milestones in between those moments. So I'll throw it out to both of you. What is it like to work on the day-to-day, getting and working towards a launch?
I can go first, Luke. I was just thinking about how I kind of feel like on test day, which is very similar to launch days, it feels like a performance. Like I am not a good stage performer at all, but I imagine what performers feel like, what artists feel like when they're on stage. And they got this one moment to make it happen, and that's a lot what it feels like to me, where everything you've done in the past, weeks, months, years, kind of culminates on this one day, whether it's testing or launching. And what people don't see that happens in those months and years is just a lot of testing. Testing your subsystems, just singular components, testing larger subsystems, and then eventually, testing the full system altogether. And I think that's one thing that I didn't realize when I started here is how much testing goes into these things. It's an incredible amount of time that you just spend designing and redesigning, testing, and figuring out what goes wrong and fixing it.
How about for you, Luke? What does that look like in between, tests and launches and, the moments, the milestones between the moments?
Yeah, well, it can look like a few different things, I suppose. But it's a lot of, it's a fair amount of reflection, and a fair amount of kind of patience to sort of think about the problems and come up with the solutions. It doesn't come quickly all the time, and there's a lot of back and forth with the team and debating the right solution and trying to make the right decisions, and analyze the data the best you can. Sometimes you don't have all the information to answer the questions, so you try to make the most informed decision you can with what you have. I like to do a fair amount of modeling and simulation and trying to predict what will happen before the test. I think we have a good balance of testing and modeling at bluShift. I tend to be a little more on the modeling side of things, but you can go too far in the weeds on that and start
When you say
spinning wheels
modeling,
of
though,
that.
Sorry to interrupt. I'm so curious about that because when you say modeling, that means different things to maybe different folks.
Yeah.
When you say modeling, what elements are you trying to, create?
Yeah, I guess I'm talking mostly in terms of modeling things like, usually it's the propulsion system is what we've been spending the most time on lately, and it's modeling the performance of the engine, usually in some sort of a coding, some sort of algorithm, usually written in MATLAB is what we use, what I use most of the time. It's a really high level language that's good for non-computer science guys. But and you you write in your sort of thermodynamic relations and the properties of the different propellants and the geometry of the motor and the nozzle, and sort of predict the different operating parameters of the motor, and then you can use that to simulate the overall vehicle performance, so how high and fast it'll go and stuff like that. And you can find balances of performance versus weight, and find these sort of optimal points, because you can usually make a motor really high performing, but in those situations, depending on the specific kind of motor, that might not be the lightest. So you could probably build a really light motor, but it's not going to be quite as efficient necessarily, depending on what kind of materials you use. But it'll be so yeah. Usually there's some counterbalance of things like weight and performance and other things like that. So trying to predict what the real vehicle and real motor will do without having to test it. But there are certain bits of information that you can't. That's really hard to predict and simulate. So things like, how efficiently does the motor actually mix and burn the propellants? Usually rocket motors are quite good at that. They're in like the high 90% range for efficiency, but that's a number that's really hard to predict accurately. So usually you would measure something like that from a test. Yeah. So I'm trying to take data from the test for things like combustion efficiency that I just mentioned, and combine that with sort of the performance that's easier to model, given some of those inputs, and then decide what the optimal move is for the next iteration.
And that's where you come in, Gerard, and take that information that Luke has modeled, and you're like, hey, we're gonna light this up.
Yeah, that's right. Yeah, Luke is pretty modest, but he is kind of the big brain of this our efforts, and kind of we usually ask him a lot of questions, and he's got the most experience with, like you said, modeling and kind of predicting what's going to happen.
Well, you need all the different pieces.
So yeah, walk us through what happens after an end. So right now we're sort of in between. We're post an engine test from before, but we're also preparing for an upcoming engine test. What goes into the next couple of weeks leading up to the engine test, and then afterwards, what happens immediately following?
Yeah, we've got it pretty down packed now as far as what happens, in the week following up to a test. But when there's big design changes, and like what we're working on right now, it's a lot of design review with each other, trying to predict what's going to happen, and trying to predict what's the best move. We're really hoping to get better performance on this next test. So there's things that need to be ordered and designed. We get them all together, and fuel manufacturing, for example, is another thing.
When you say performance, when you say you're trying to get better performance, better performance than the previous test, better performance than what was modeled, before? What do you mean by that?
Yeah, there's performance markers that we're trying to hit for our launch, where we're trying to hit a target altitude, um, and a target mass to that altitude, um, and yeah, there's also performance compared to previous tests, and you can kind of think of it as a rocket engine, even though a hybrid is a lot simpler than a liquid engine. You can imagine there's just a big switchboard, and we're kind of like trying different things, plugging in different wires in different places, that eventually affect how the vehicle is going to perform. So there's a lot of kind of discovery and um, detective work trying to figure out what's going to help us the most.
Yeah, and specifically in this case, there's a specific combustion efficiency that we are targeting that we know so it's hard to model what we will get, but it's easy to say we need at least this to reach our goals. So we've been honing in on that combustion efficiency number, and another thing that we've been working on is trying to improve how smoothly the engine runs in terms of oscillations over time. And we call that stability. So we're trying to make the burn stability better. So those are two specific things that we're working on.
Yep. This test that's coming up, but we're going to do a preview of it, in a future episode. But, generally speaking, how are you looking to balance the potential performance, reliability, even manufacturability of what comes out of that test? Or is that something that you're isolating certain elements for this test versus previous attempts?
There's always the real world boundaries of, there's physics boundaries, there's economic boundaries, there's logistics boundaries, and so that kind of drives us in some way. And yeah, what would you say, Luke?
I think a philosophy that we've had since the beginning is to not. We have aspirations of using all the cutting edge materials and tools that we have at our disposal, all the fanciest carbon composites, and anything else that we could potentially use. Like, we are working towards using all the fancy tools, fancy materials, but those all come at pretty significant costs and usually timelines, because they're not as well understood and integrated. So we've tried to use really well understood, available, simple materials that keep costs really low and keep timelines moving, but make sure that we use them in the most optimal way. So, for example, we're just using stainless steel for our oxidizer tank and combustion chamber, which by every metric, you could build a composite COPV, an overwrap pressure vessel that has better performance, but would definitely increase costs and timeline at the moment. So as long as we're designing with stainless steel in mind, then you can still reach the goals that we need to reach, as long as you're smart about it.
Will
So,
that
for example,
eventually affect? So if you switch over to the composite later,
Yeah.
you'll have to do a test with that other composite, right, before it
Yeah.
actually launches. And then will that actually increase the timeline? And you should, or should you just go with stainless steel in the beginning?
Well, that's a good question. I mean, yes, when you're switching over, you would have to repeat some tests, but a lot of the hardest problems to solve will be solved regardless of which material you use. You just have to sort of change your operating point, which you should test, but a lot of your learning with the stainless steel should carry over to the new material. You're going to solve a lot of the same problems, but you just need to make sure that you're running the engine at the correct, like I said, operating point. So for example, if you run your engine at a high combustion chamber pressure, the engine will be more efficient because it's running at a higher pressure. But your engine will be heavier because the pressure vessel has to be thicker to contain the pressure. So there's a balance where you increase the pressure, you get more efficiency, you get better vehicle performance, but then your vehicle is heavier, which hurts performance. But if you go to too low of a pressure, you're really going to have a very light vehicle, but a low performance engine. And there's an optimal point there. And making sure that you're running at that correct point is what I'm talking about. So then when you go to a lighter material, you can run at a higher pressure. And since the material is lighter, you can run at that higher pressure without having the weight penalty. So you would want to test at that higher performance point.
Yeah.
But things like stability and even combustion efficiency aren't too affected by that increase in pressure.
Yeah, got it.
Yeah.
Thinking about the engineering, and I love how you going into some detail without giving away, the secret sauce here. But it's really great to hear about the internal elements that you're thinking about working towards, and even the milestones that you're hoping to achieve at each one. And often, from the outside at least, in the layman's, as I sit here, often, you're thinking about the engineering kind of being like a straight line from the concept to the solution, meaning, from the idea on the napkin and hey, this could really work, to actually seeing it, be tested in the lab and outside, and then eventually to a launch. How much of the process is actually this iterative, peak and valley, where you're like, one day you're on top of the world and you got the whole, all the problems solved. And then you come back the next day and you're like, shucks, we missed something. Or, what happened? How much of that happens?
Yeah, I'll let Gerard take this one, but I'll just say first, like, I think at least I'm always aware that we have a ton of things to still figure out. So it's more of the peaks are more like we achieved this goal, and then the valley is like, oh yeah, well, we still have 99 other things. So the reality hits, the couple days after the test, or something like that.
99 problems, but the X isn't one, right?
Yeah. But
Gerard, I don't know. I think I feel like I'm sometimes the most optimistic when it comes to testing. Like, if we get through a test day and nobody's hurt and everybody's safe, then that's a peak. That's a super huge. Even if we didn't hit our numbers that we wanted to hit, all things aside, lighting a fire like that is second to none. And
I mean, I don't think OSHA's listening to this, so I mean, you can,
Well, yes. Well, no, but safety is, actually huge for us. It is a really a big part of what we do. So OSHA, regardless.
Well, I think that's why you're basically saying that is like the entire week or two leading up to a test. It becomes less of a figure it out step by step thing, and it starts to morph into follow the procedures and go by the checklist, and it becomes more of a performance that has been rehearsed. You do all the sort of the engineering work ahead of time that's different every time, but then as the test approaches, that morphs into, it's just kind of a train leaving the station with the procedures that have been in place for dozens of tests, and that have been vetted and gone over hundreds of times to sort of to make sure everything is done safely. So like at the end of the day, that is the a successful test is a safe test, and there's a ton that goes into that. So that's very gratifying just to sort of, have a good performance, right? That you've rehearsed and put a lot of time into making sure that it goes off well.
Yeah, data is everything. It's the only way that we can do this. It's the only way that we can learn. So as long as we're collecting data, no matter how the test goes, we're good. We'll figure it out. We'll find a solution. Your prompt also, Justin, was reminding me of the first time that we tested with this 24-inch motor. It was like the dead of February, and we were trying to do a test before March, and we're out there in the negative 10-degree weather trying to get everything going, and then we go to test, and sure enough, something goes wrong, and we got to go back to the drawing board, and we even get a fire going. We had to scrub, and
we did do our first test March 1st, though, I think, right?
Yeah, we just made it.
Yeah.
And that kind of in the earlier days with the when the technology was really new to us, that would happen a lot more often during tests where there's just something new that hits us. And that was kind of like the most grueling days, but also the most rewarding afterward, to be able to figure out what went wrong and achieve a test. And now it's a lot more methodical. We have so many procedures that it's just going through a procedure line by line, and backup procedures. And I think a lot of people don't realize how much time goes into just those documents, just procedures, and
there's so when you're working on something this complicated, you have to start just writing down lists of valves to check and orders, and which is, anyone who's done this is sort of like, no duh. But I don't know if everyone realizes, when you've got 100 valves, you need to write down, you go from this state to this state, and this is what you do to go from state A to state B. And because you just simply can't keep track of it just in your head. It has to all be written down.
All right, so I'll get you guys out of here on this one, and that is, what are you most proud of so far in terms of milestones and the innovations that you've worked on relative to the engine, the propulsion system, and really just the overall development of bluShift?
I'm super proud of when we run tests, where we're at right now, where we've run 4 full duration 60-second tests. That is a pretty substantial accomplishment. And how everybody comes together as a team to pull that off is the best part of it.
How about for you, Luke?
Yeah, I mean, I'll second that, and just add that I think we've done a good job keeping our eyes on the ball in terms of, we've had the suborbital flight that we've been working at for pretty much as long as I've been with bluShift, and we've done a good job incrementally working our way there through the 6-inch motor, and then formulating the size motor we're going to need to do the suborbital starless rogue flight. And at the time, we optimized it so that we could use those motors for orbital vehicles. And whether that's the direction we end up going at the end of the day is me a little bit up in the air, but it's still the best choice for the suborbital starless rogue. And this sort of staying focused and sticking to our principles, our design principles and philosophies, and then running a lot of successful, safe tests. I think, I don't want to jinx anything, so I'm not gonna say anything more than that. But we've I think we've been really careful and methodical, and really stuck to our philosophy of how to tackle this problem as engineers.
Well, that's awesome, guys. I really appreciate you joining me on this episode to go inside the build and kind of peel back the fuselage, if you will, on what goes into the engineering of the rocket motor right now. It's pretty cool. So I really appreciate you guys joining me.
Yeah, it's been fun to talk about it.
Yeah, thanks, Justin.
Well, we'll have you guys back for the next episode as well, where we'll actually talk more about what it takes to make this thing fly. On behalf of my guests today, Luke Saindon, the lead mechanical engineer, and Gerard Desjardins, the lead propulsion test engineer for bluShift Aerospace. You've been listening to the Throttle Up podcast. Till next time.